So now let us welcome our second speaker, Dr. Jiaju. Dr. Qi received his PhD from the University of Guelph in 2025. He is currently a research and development engineer at Xi'an Kunlun Industry Group. His research focused on the intersection of artificial intelligence and industry systems. Today, he will present a talk, Optimization of Electric Bus Charging Schedule based on hierarchical deep reinforcement learning. Please join me in welcoming Dr. Qi.
Hello everyone. Today I will introduce my research. The name is electric bus charging scheduling based on deep reinforcement learning. My name is Jiaju from Xi'an Kunlun Industry Group. Nowadays we know that the greenhouse gas emissions are very large, and the transportation parts accounts for a very large proportion. So that leads to the widely use of the electric car. They are very convenient and fast to charge, and they are very economical and environmental friendly. These are the advantages of the electric vehicles. So in my research, I want to build a sustainable transportation system with many electric buses. We can see this picture is the charging station in the campus of the University of Guelph, and we consider there is a charging station, and there are many chargers in the station, and all the EVs are charged in the station. So it leads to the EV charging scheduling problems. That is EPCSP. The question is how to charge, how much to charge. For example, if one EB go back to the station at night, and it will leave the station according to the bus schedule at 9:40. So it means it has 40 minutes to charge. So we want to know how much to charge. For example, charging to 100%, 80%, and so on. And also, if we have many electric buses and we want to decide which one to charge. Our objective is to minimize the operational costs, and also we also want to guarantee there are sufficient battery energy in the EB to complete the joint trips. In our model, we consider there are three false uncertainties. The first one is the traffic condition. For example, at the peak time, at the rush hour, there are many bus vehicles on the road, so the bus will should have more time to go back to the station. And the other one is the electricity prices. We want to charge the bus when the price is very low, and sell the energy back to the grid when the price is very high. And the last one is the PV output power. We want to use clean energy, but the power is flexible all the day. For example, at afternoon, the power is very high, and the other time the power is low, and at the evening, the power is zero. There's no PV output power. That leads to the DRL methods. We know that DRL is very suitable to handle these uncertainties. It has several advantages. For example, DRL can learn directly from the interactions with the environment, and the DRL has strong adaptability in dynamic environments, and it can make decisions quickly in real time during the deployment phase. But we also have many challenges in our research. The first one is the uncertainty we have introduced before, and the second one is the long-range multi-phase planning with birth and rewards. We want to make decision for all the EBs at one whole day, and there are hundreds of the time steps, so it has this challenge. And the third one is the multi-level temporal abstraction. We should make many levels of the decision. For example, we want to make the charging target for example, at per hour, and the charging power decision at a very finer time scale, for example, 10 minutes. So we also met this challenge. And the last one is the critical safety constraints. And we will use the CFR method to handle this challenge. Now this is our first research. Uh, in the first one, we consider a very regular environment, a very simple one, with just one single EB, and we also consider the sufficient charging resource in the model. And we also use the V2G mode, that is the vehicle to grid mode. So it means the EB can sell the energy back to the grid, and the time horizon is one whole day. You can see the system model, this research, each EB has two periods. The first one is the charging period. You can see the EB are charged in the charger, and the grid, electric grid, will it can purchase the energy from the grid, and according to the schedule, the EB will leave the charging station and travels through the bus route. So this is the operating period. So in this research, our work will use the theoretical DR model to solve the problem by defining the options. And we should also decompose the original MDP into a novel two-level decision process. For example, the high level is the semi-MDP. It will make the decision of the charging target, and the low level is the regular MDP, and it will make the decision of the charging power. And in this research, we also propose a new algorithm. This one is the definition of the options. This is presented by Saturn, a very widely used framework. You can see in the regular MDP, the agent make the decision every time step, and the semi-MDP, it can span many steps, and the options over MDP combine both. In our research, we define the options as the charging target. So it means when the EV go back to the station, it will make these decisions at the high level with the mu policy. The omega is the charging target. For example, it decide to charge the 100%, and then the 100% will input to the low level agent, and it will know, oh no, I will charge to the 100%. So I will charge much more power in the electric bus. And our algorithm use two DD-queues at two levels. So the name is theoretical DD-queue, and the HER is a trick to improve the data efficiency. And here you can see the results. First, the battery trajectory curve of our algorithm flashes much more than that of the other ones. And the HD HR can realize the charging target in every period. Now, we will go to the second research. In the second research, we improve our environments. For example, we will consider a large fleet of EBs, and we also consider the limited charging resources. That means the number of the chargers is less than the number of the electric buses. So it means the bus should make the decisions of which one to charge, and it will cooperate to do the task. And in this problem, we also incorporated the PV generation in the system model. Here you can see the PV can also provide the energy to the chargers. So we have two improvements. The first one is to change the definition of the options. If we have one single EB, we can make the decision of the charging target. But there are many EBs, for example, 20 EBs, so the action space will be very large. Now we change the options to the charger allocation. And we also improve the theoretical framework. In the last research, it is the options over MDP. The high level is the semi-MDP. Now we change to the high level to the MDP. So the name is the DAC framework. And we also use another algorithm. The PPO is very also very widely used and a very popular algorithm. So at the high level, it is a centralized agent, and the MVP solved using the PPO algorithm. And the low level is the decentralized agent. It means we will treat each EB as an agent to decide the charging power for itself. And so we use a multi-agent PPO algorithm in the low level, and our algorithm named DACMA PPO. And we also use the parameter sharing technical in our research. And then we want to add some other methods to our research. That is the CPR. So we formulated the problem from the MDP to the constrained MDP with options, and then decompose it to two augmented constrained MDPs. And then we also added the Lagrangian relation method into the DSM framework. So that means we bridge the gap between the CFR and the HR. That is the DCME PPO algorithm add the Lagrangian relation. So we have the DCME PPO Lagrangian algorithm. And our methodology is to change the reward function. In the original MDP formulation, we know that the reward function has two parts. The first one is the operational reward. It means how much to charge, the charging cost. And the second one is the negative safety cost. That means if one EB break down on the road and with zero energy in the battery, we will add a very large negative number to the reward. For example, negative 1,000 and so on. And here we use the constrained MDP formulation. We just use the treat the reward function as the operational reward. And the negative cost, safety cost will change to the safety constraint. Now is our methodology. Now we use five networks. The first one and second one is at the high level. Is the high level actor network and the termination condition network. This one means when to stop or terminate the high level options. For example, at 9, we will choose the bus 1 and 2 to the chargers, and then we will sample this probability. It will output the probability. If we sample for example is 0.9 the probability, and we will stop the high level the high level decisions, and has another one. For example, we will choose 1 and 3 these two bus to charge. And the other one, the other three networks are at the low level. The first one is the low level actor, and also the reward critic and the cost critic. We share a pair of the critic networks at the two levels, and we also use the PPO algorithm. So the PPO lag region solve the high level CMDP, and the MA PPO lag region solve the low level CMDP. And then we has uh, but two algorithm as our benchmark. The first one is the MLP under the stochastic setting, and the second one is the DCMPO for the original MDP without any CFR methods. And we use three data set. All of them are public data set. The first one is for the electricity process, is a method from the USA data set. And the bus schedule, we use the Canada data set, the Guelph transit, and the PV output power data set collected from the Brazil. We have two performance metrics. The first one is the average operational return, and the second one is the safety violation rate. So this is our environmental results. We know that we can find the our proposed algorithm show the best return, and then we can see for the safety rate, our algorithm achieve a near zero average violation rate. And this is for the training performance curve. So they are based algorithms. In the future work, we want to expand our environment. Now we consider just one station, and in the later work, we want to consider the city level environment, and with for example, three stations. And then we also want to research the joint optimization of the charging infrastructure and the transition, the scheduling. For example, we want to make the decisions of the number of the chargers and when where to the location of the chargers. And the third one, we want to use some more energy resource, for example, for the wind and the other ones. And then we want to also use some more safer methods, for example, the MPC and the shielding and some other ones to our research. Thank you, everyone. Thank you very much.